Now let me return to part of speech tagging and say a little bit more about how sequence models perform and what kind of features end up being used and useful. So what are the main sources of information for part of speech tagging? One source of information is knowledge of neighboring words and their possible part of speech tags. So if our sentence is, Bill saw that man yesterday, we have a lot of part of speech ambiguities. So Bill can be either a proper noun or a verb. Saw can be either a noun or a verb. That can be either a determiner or what's tagged as IN when introducing a complement clause. Man can be a noun or a verb. But at this point we start to notice that there are some constraints from neighborhoods. So it just can't be the case that that is a determiner but it's followed by a verb, that this is a bad sequence. And so this is sequence information that gives us some ideas as to how to part of speech tag things. And when people started working on part of speech tags, people thought of that as the main source of evidence. But it turns out that that's not really the case, that the easiest and biggest source of evidence is statistics, knowledge about how often words have different parts of speech. So we can also get a long way by just saying man is very rarely used as a verb, and therefore just without even looking at the context we probably should take the part of speech tag noun for man. And that latter source of information proves most useful, but that's not to mean that the first source of information isn't also useful. So what we're going to want to do is start putting more and better features into our maximum entropy tagger, producing a feature-based sequence model. And one part of that is just features that we can define over the word itself. So knowing what the word is useful, but it turns out you can get a lot of further value, especially for rare and unknown words, by also putting in features that pick out properties of words. So looking not just at the word but its lowercase form. So maybe there are many words that we haven't seen capitalized at the beginning of a sentence, but if we know what their lowercase form is and its parts of speech are, then that will help us. Knowing the beginning of a word, so if you know a word starts with UN, that gives you a bit of information about what its part of speech is. Knowing the suffix of a word, so if you know a word ends in ly, it's almost certainly an adverb in English. Capitalization is useful, so in English the capital letter, once you're away from the beginning of a sentence, is a very good clue that you've got a proper noun. And here's an interesting different kind of feature that we've made a lot of use of in some of our Stanford systems. We call these word shape features, an idea first suggested by Michael Collins. It's a different way of making features from words that creates natural equivalence classes that is very useful for generalization. And so the idea here is that you're mapping a word into one of a small set of equivalence classes that represents its shape. So here what we're doing, and there are different exact schemes that you can use, we can say this is a digit character, this is also a digit character. Let's collapse for our equivalence classing sequence of characters are the same. Then there's a hyphen here, and then we've got a sequence of lowercase letter characters. And so we will give that the word shape of D-X. Some number of digits, followed by hyphen, followed by some number of lowercase letters. And that kind of feature proves to be a very useful feature in quite a few of our discriminative models. So here's the headline good news. If you get clever using all these kinds of features and just build a model that looks at the current word and assigns a tag to it, it turns out that without looking at the context whatsoever, you can build a part of speech tagger that overall gets 93.7% of words right, and actually does quite well on unknown words as well. Commonly we pull out separately the accuracy for unknown words because it's always lower and can be distinctively different from the accuracy for known words. So here are some figures overall just to give you a picture of the kind of accuracies you should be expecting from part of speech taggers and how different features impact the classification. So we discussed before this idea of a baseline method of just giving the most frequent tag to words and calling everything else a noun. So overall that gives about 90%, but only gets about half of the unknown words right. The next set of models that people looked at were HMM models, hidden Markov models, which I'm not really going to cover in this class, but this was sort of in the mid-90s, the state of art of part of speech tagging, so that got around 95% of all words right and did just a little bit of better on unknown words. We just saw on the previous slide that just having a straight classifier, no sequence model, but with rich carefully chosen features actually works rather well. It does much better on unknown words and doesn't actually perform badly on known words. But people have gone on from there. The idea that you could use features to do a better job was able to be incorporated into hidden Markov models as well. And so Torsten Brandt's produced this high-performance hidden Markov model-based tagger, but which used feature-based ideas for predicting unknown words, and that performed rather nicely, so it gets around 96.2% overall and very competitive performance on unknown words. But you can keep on building features into your maximum entropy Markov model, including using context features that we didn't have in the first model. So then if we go into a sort of a standard maximum entropy Markov model tagger of the kind we've discussed, that might be getting almost 97% on all words and starting to do a bit better again on unknown words. And that work has been pushed up further at several places, including at Stanford. So in Stanford we have a model that's almost like a maximum entropy model, but allows some bidirectional dependencies, and so that's then pushing the overall accuracy up to about 97.2% and pushing up the unknown word accuracy further to about 90%. And that's getting close to how good you can expect part of speech taggers to perform, because for reasons of humans themselves not being sure what the right answer is to part of speech tagging problems, and also just because the gold standards have errors because sometimes humans goof and put in the wrong part of speech tag even when it seems like the correct answer is clear, that it seems like around 98% is the upper bound of what you could possibly hope to score on the kind of test sets we have for part of speech tagging. And if one wants to keep on working on improving things, normally the way one goes about that is by staring hard at the output of your part of speech tag or whatever it is, and looking at where it makes errors and thinking of ways in which you could encode some information into features that would let you detect that something has gone wrong and get the system to prefer some other configuration. I'm just going to give an example of that now. So here we have an error of the part of speech tagger, that there's the word as, and the part of speech tagger has chosen the preposition tag for it, whereas what it should have chosen is the adverb tag, because this is as soon, modifying soon. Well, how could we fix that? Well, it seems like the information that we want to use is that if the next word is soon, that's a really good clue that as will be functioning as an adverb. And so we can fix this error by adding a feature that looks at the next word. So we're using next words as well as previous words and previous part of speech tags. So here the part of speech tagger for intrinsic has labeled it as a proper noun. That's a common error, because if the part of speech tagger sees a capitalized word that it never saw in the training data, normally its first best guess is to say that's a proper noun. But that's not necessarily true at the beginning of a sentence when all words get capitalized. But maybe we actually know about the word intrinsic, and that was seen several times in the training data, and we know that it's an adjective. So if we could utilize that knowledge, we'd be able to get this case right as well. So if we put in a feature of what's the word lowercase, that feature would argue that this word should be tagged as an adjective, and so we might be able to hope to fix that error. Note that both of those features didn't require any sequence information. We were looking at features of word to the right and what's the lowercase form of a word. And that's an interesting general observation. In early work on sequence models, people were very fixated on sequence models and using the sort of sequence of labelings, the sequence of tags to predict other tags. It turns out for many of the problems that were and are conventionally done as sequence labeling, that the sequence information is barely useful. It normally gives you a fraction of extra performance, but very, very little. And so we already saw in the case of part of speech tagging that just using this model of using a lot of features of the current word to predict the tag performs very nicely. So that gave us this performance of 93.7 on all tokens and 82.6 on unknown tokens. But you can do a lot better than that, as was being suggested on the previous slide, by also considering things like what's the next word and using that to influence the tag, and what's the previous word and using that to influence the tag. And so that's what's being referred to here as the 3 words model. So you're having features independently of these 3 words influencing the tag. And it's actually quite stunning how well that performs. So that gives you a token accuracy of about 96.6% and an unknown word accuracy of about 86.8%. And the thing to notice is that that performance is actually quite similar to the performance you get with sequence models. So if we go back to the performance here, that you can see that that performance is very close to the performance that's being listed here for the MEM tagger. 96.9, 86.9, 96.6, 86.8. Fractionally below, but exceedingly close in performance. Okay, so what we've learned about part of speech tagging is that by itself, changing from generative to discriminative models doesn't give a big boost to part of speech tagging performance. The big boost comes from being able to put in lots of features of observations and combine them together in a good way. So that's things like suffix analysis, word shape features, lowercasing, things like that. So this additional power from having rich features has been shown to result in major improvements to the accuracy of sequence models. There is some cost, and the cost, as you'll probably find out in the assignment, is that training discriminative models is just much slower than training generative models. If you remember back to language models, well, you can estimate language models essentially just by counting data, whereas for discriminative models, we have to do processes of numerical optimization, and they just are much more time intensive. That completes the discussion of part of speech taggers, and so now you should be in a position not only that you understand something about part of speech tagging, but in general how to apply maximum entropy sequence models to part of speech tagging and other similar sequence problems.